Hi there, and welcome back to our discussion of matching queries and indexes. Establishing a good connection between queries and indexes so that we can identify the indexes that can really help us with particular queries. So if a query sports a predicate that refers to multiple columns, then we could of course create indexes for each of these columns individually. But another option would be to create a so-called composite index, or sometimes even called a concatenated index, right? And concatenation actually is the name of the game. We would use a create index statement that looks like this. We would name all the columns which should be the indexing criteria in this list, in the parentheses here in the create index statement. Formerly, we only had a single column here in such a list, maybe the column C1, maybe even an expression with expression-based indexes. Now it's this list. It's really an ordered list of column values here. And these lists of values, these will make for the ordering criteria that is being used to construct and then also to search the B plus tree, the resulting B plus tree. So while it's probably obvious how rows should be ordered or index entries should be ordered in a B plus tree that is only organized with respect to a single column, one has to be a bit more careful if the ordering criterion is now built from these multiple columns. And the answer of the B plus tree structure is that the rows or the index entries inside the index will be ordered lexicographically. All right, so that would be the normal lexicon order that you all know. All right, so given two rows, T1 and T2, how would they be ordered by such an index? By a C1, C2 up to Cn index. Well, lexicographic ordering would first compare the C1 values of these two rows. Maybe these two rows already disambiguate everything, and we know that T1 is smaller than T2 regarding C1. If this is not the case, if C1 is not different in these two rows, if C1 cannot decide which of the two rows is smaller than the other, well, then we would look at the second criterion. Okay, well, maybe even the second criterion, the further criteria are all equal. So we would end up in a situation like this. So all of the criteria, all of the columns are actually equal in the two rows. Well, then we would look at the very last, at the Cn column, to decide whether T1 is actually smaller than T2. So that would be the normal lexicographic ordering. As you can see, there's some order involved here, an order of criteria. It's really that C1 is the first and Cn is the last ordering criterion. This is actually expressed by this the construction of this Boolean formula here that first considers C1, and only if C1 cannot decide the inequality, then C2 is considered, and so forth. Okay, so it really makes a difference whether we mention C1, C2 up to Cn here, or if we jumble this order and consider the columns in some different order. That's even and already apparent if we look at these two simple indexes, concatenated indexes over just two columns. The row order in an index built on C1, C2 will be different in general from the row order in a C2, C1 index. Okay, and since we know that the row order makes all the difference in index construction and the exploitation for query evaluation, this makes these two indexes that may look similar behave completely differently. Okay, we will have a closer look at these differences in a minute. This is even also the case for these two indexes. Consider indexes built only on the C1 column and a composite index on the C1 and then C2 column. In this index, two rows that agree on their C1 values will be inserted in some order. Well, it's actually not determined by the index criterion which row will come first in the index. in this index, 2 rows that are equal regarding their C1 values will then be perfectly ordered by their C2 values. Only if C1 and C2 are actually equal, then there will be non-determinism. All right. So even in this case already, the index, the row order in the index might be different. Okay, maybe this becomes more clear if we look at a particular depiction of the resulting order of rows inside such a composite index. All right, you will see such diagrams that look like tables but are actually being used to display the order of entries, inside an index. You will see these all over this particular chapter. Okay, I hope that they are readable and convey the index order in an intuitive fashion for you. Okay, in these diagrams, if you look at these black bars, they just represent the magnitude of the values. Okay, so what we can see if we organize the index according to this column concatenation, so first C1 and then C2, this will be the row order that we observe in such an index. All right, the rows with the smallest C1 values, they will all gather at the beginning of the index, at the left-hand side of the sequence set, in a sense. Okay, so this is where all the C1 values will gather. Rows that agree in their C1 values, which is exactly this particular group of rows, well, they will be ordered according to their C2 values. So the smallest C2 value will be found at the beginning of this group. The largest C2 value will be found at the end of this particular group. Inside the group, the rows agree on their C1 order. I'm using the group in quotation marks here, since we are not really talking about grouping here. It's just a cluster of rows that agree on their C1 value. All right, so once we have seen that cluster in the sequence set, we will see the cluster of rows which have a larger C1 value. All rows that agree on this C1 value will then again be ordered by their C2 values, and so forth. Okay, at the end of the sequence scan, we will find the rows with the largest C1 value and, of course, also the largest C2 value. So that would be the ordering of rows that is being created in this particular index, and that ordering of rows will of course be different if we switch the order, if we swap the order of these columns. Okay, what we will also see is that rows with a particular C2 value, say regarding the rows regarding a particular C2 value V here, let V be some value in the domain of column C2, well, we will find these rows all over the sequence set. Well, there will be probably a row with C2 value equal to V here, and it will be, let me be more focused here, and it will be here, maybe down here, maybe even up there in the C2 group. There may be some, or maybe only a single row that has a C2 value of V. So using this as an index condition, on its own will make us search the entire index for possible entries of rows with C2 value equals to V. We would have to scan the entire sequence set to find these values. And as such, the index would be, I think, worthless. It's different for the C1 order. Of course, if we scan the sequence set from the beginning to the end, we will see strictly ascending C1 values. And looking for a particular rows with a C1 value of, say, W, will probably define. Will probably define a very well local search window or a subset of the sequence set that we have to search. Okay, so that's what we expect and what we hope for in index scanning. Scan only a particular little window inside the sequence set. This is entirely different for C2, which will lead to some hits there and some hits there and some hits there. The index would be worthless at this particular point. All right. This leads to this very important observation here in this box. Now it's boxed. Such a composite index with multiple columns is useful to evaluate predicates that refer to a prefix of that column list. All right. So a prefix of that column list may only be C1, and we can indeed use this index to identify rows that have a particular C1 value. All right, because this is the primary ordering criterion here. We could also use that index to identify rows that have a particular C1, C2 combination. Okay, that would narrow down the search window or the subset of the sequence set that you have to consider even more. Very good. But it would not work to evaluate a filter predicate that only refers to C2. We would have the jumping and the looking around the entire sequence set width here, as we've just described. Okay, so this is the key word here. The prefix of the column list is something that the search or the filter predicate, the index condition, has to refer to. Then we can make use of this composite index. And this is exactly the behavior that you will find inside PostgreSQL. Let me show you. Over to the terminal here. Okay, so of course we will talk about our indexed table now, but we are not interested in the index on column C or this expression-based index. So let's remove these first. Gone. All right, let's see what's the state of the table now. Okay, so we still have this primary key index here on column A. So for the purpose of this demonstration, let's even remove this particular primary key index. Okay, so that would be the SQL command to remove this particular key index. I would just drop the primary key constraint, and that would also drop the associated primary key, B+ tree. What we want instead is this composite or concatenated index on columns C and A in that particular order. This is the CA index, and it will be different from an AC index. Okay, so let's create this stuff. Drop the primary key already. Now building the composite index. Okay, wait, and then analyze the situation. Okay, doing the analysis now. All right, so let's see what the state of the table now. Yes, there's only one index defined, and it's the composite CA index that we've just talked about. Very nice. Okay, so now this is an index in which the keys, the separators, for example, and also the entries in the leaves of the B+ tree, they already carry 2/3 of the column. This table only has 3 columns, and 2 of the 3 columns are already present in the index. Can we still hope that the index is indeed smaller and more compact and thus more efficiently searched than the table index itself? Just to make sure that this is indeed the case, let's look at the number of pages that the table itself and this composite index are now occupying. And you see there is still some substantial space gains to be had here. All right, so indexes are indeed still more compact. We are missing the B column, for example, in the index, and the B column is the very wide or the rather wide textual column. So there's some space savings to be had. I would rather search this more compact data structure that is organized by a CA order than performing a sequential scan here in this table. Okay, so that's okay. So now let's see how the CA index has indeed ordered the rows inside the indexed inside the sequence set of the index. So it's not easy to actually look at the sequence set of the index, but we could just simulate. We could just simulate the order of this index entry in that we just used this order by criterion that directly mimics the C, A order of the composite index that we've just created. So the order of the rows that is being output by this particular query matches the order of the entries in the sequence set of the indexed CA index. All right, only to have a visualization, to be really clear about the order in which the entries in the composite sequence set index are now present. Okay, and we will see that indeed the sequence set starts with the smallest C values first. All of these smallest C values, the first 20 at least, are -1 here. And well, if the C value cannot discern the individual rows and determine row order, well, then it would be the A value that we look at. And you indeed find the row with the smallest A value here at the front, then the next largest A value, and so on. The A values are increasing within this C group here. Okay, so this is one of these C groups, the -1 C group that we have also referred to on the previous slide. Okay, so such an index is now present and available to us. And if we evaluate a query like this, where the index predicate indeed refers to a prefix of the composite vector, the composite list of columns, the C, A column list in the example. This is indeed a prefix of the list C, A. So we would expect the index to be useful. It could be used even though the A column is not mentioned here in the search predicate. Okay, so we expect the index to be used, and indeed it's being used. All right, and you can see the number of pages that were actually hit by the sequence set scan. It's actually a small number of pages. Only 16 pages have been hit by the sequence set scan, and also by the traversal down from the root, but these are only 1 or 2 pages. We have hit a rather narrow window, a rather narrow C window. All the rows with C value 0.42, they have been identified during the index scan and then returned to the caller. Okay, so since this is a bitmap index scan and bitmap heap scan pair, we know that this particular bitmap index scan only creates a bitmap of potential hits. As you can see, the bitmap index heap scan, the second phase, the bitmap heap scan, then uses the bitmap to collect the matches from all over our heap file, our table heap file, and you can see that, well, it reads and hits quite the number of pages around our heap file. Okay, so that's because, well, the indexed file, our index table, is not clustered according to the C values. Okay, that would be expected, but well, in the index at least, we have locality. So all of the C values inside the index with value 0.42, they have been found on very few pages. Okay. Things, of course, look entirely different if we use this predicate here. And this predicate is referring to a set of columns that is not a prefix of the composite C, A order. All right, so we are looking only at this rightmost column A here. And as we've seen on the previous slide, the rows with values A equals 42, they are expected to be found all over the sequence set. This is why PostgreSQL refrains from using that particular composite index at all. It would rather just sequentially scan the table heap file itself and not bother involving the index. The index would lead to additional I/O, entering at the root, traversing the tree, and then traversing all of the sequence set anyway, only to be then guided into the heap file at random locations. There is nothing to be gained and nothing to be had from index presence here, so we would rather ignore the index and perform a sequential scan at this particular point. The index does not match the query, so it's not being used. Okay, well, we could trick or force or arm twist the system into using index scan. So in this case, the bitmap index scan that we've seen above. All right, so we could forbid the system to use sequential scan and to also forbid to use index scan. All that's left now is indeed the bitmap index scan. We would force the system to do this against our best knowledge. So kids, don't do this at home. This is only done here for presentation purposes. Okay, so what happens if we do this? So we force the bitmap index scan and indeed pose a query that does not match the index. Okay, of course we suffer the consequences. Okay, so execution time is disappointing, and this is what we see when we perform the bitmap index scan. Do you recall that we only hit like 15 or 16 pages during an index scan that really matched the query and the index? Now we are hitting, I don't know, I think we are hitting all of the pages in the sequence set of the index. Of course we do, because well, this index is not organized by AL values. AL values are to be found all over the sequence set. So we gain nothing by scanning the index. Quite the contrary, we only involve more IO that we could have saved. Okay, indeed, this is a very nice example, I think, of queries or of a situation where it really makes it different whether the query and the index match. And the system has some built-in knowledge about that. In this case, it's the knowledge about the prefix of columns that has to match the concatenation or the composition of index criteria that we have used to construct the B+ tree. So let's quickly redo that and return to a sane situation here. Okay, so I think that's about it. That's about the matching of queries with composite indexes. Okay, again, we have only touched the surface here. There's more cool stuff to be seen and learned in the upcoming videos. So I will be there. Maybe you will be too. See you then.